Today, we want to continue looking at solving equations, and we have a very simple brief to get started on this, and that's to read the expression, then do inverse operations in reverse order. This is less of a new thing and more of a variation on something we might have been told before in an algebra class. That is to do the same thing to both sides of the equation to maintain balance. The part that I'm adding to it is the read the expression at the beginning, because it matters what order we undo the things that we see in the expression. So that's the piece that I'm adding to this by making sure that we can carefully read the expression. So let's talk about some of the extra things that go along with this. First extra thing is that the inverse of an exponent is a reciprocal exponent. I lead with this one because we know that the inverse of addition, addition and subtraction are inverses. We know that multiplication and division are inverses because we spend a lot of time with linear functions. So we want to add, since we've added exponents to our operations, our list of operations, we need to know that the inverse of an exponent is a reciprocal exponent. So I have x raised to the third power, if that's equal to 5, then x is 5 to the 1/3 power. So the inverse of an exponent is a reciprocal exponent. If, for example, I had, let's say, x to the 2/3 power, and that was equal to 5, then to solve, we would say we would take 5 and raise it to the reciprocal exponent. And then once we start getting into things like the square root of 5, we will need a calculator. So 5 to the 3/2, 11.180. I'm going to be rounding to the nearest thousandth just because I had to pick somewhere to round to. 1.180. Usually in these problems, I will ask you to round to the nearest thousandth. I will ask you for an approximation to the nearest thousandth. So these are approximations. And as is usual, I will abbreviate my approximate. I will approximate the word approximation with approx. So I'll round it to the nearest, I don't know, 2 syllables. I don't know how rounding words works. Am I rounding this to the nearest 2 syllables or rounding it to 6 letters? I don't know. But the important thing is that the inverse of an exponent is a reciprocal exponent. So if we start out, if we have x to the third, then to get it to undo this exponent, we use a reciprocal exponent, 1/3. If x is to the 2/3, then we use a reciprocal exponent, 5 to the 3/2. We just grab the calculator and ask the calculator for an approximation. So let's move on to number 2 thing. So we know that the inverse of an exponent is a reciprocal exponent, and then we also want to add to this our fraction exponents. So radicals are fraction exponents. This is where we read the index of the radical as the denominator of the exponent. The index of the radical is the denominator of the exponent. And this we can combine with our inverse of an exponent is a reciprocal exponent. Once we start taking reciprocals of things, we're going to start ending up with denominators. But the index of the radical is the denominator of the exponent. So if I wanted to solve an equation, for example, If I have an equation that says the cube root of x is equal to 5, I'm reading this cube root of x as an x to the 1/3 power. So I'm reading this as x to the 1/3. So my equation says x to the 1/3 is equal to 5. And then that tells me I need to use, since the inverse of an exponent is a reciprocal exponent, that tells me I need to use the reciprocal of 1/3 and say that x is 5 to the 3rd power. So the reciprocal of 1/3 is a 3. And so here we get 125. So this one came out with a nice exact answer. So when we're solving radical equations, we want to read the radical part as a fraction exponent, where the index of the radical is the denominator of the exponent. Similarly, our second equation up here, x to the 2/3, could have been presented to us as a radical equation. So this could be the cube roots of x squared is equal to 5. So we would read the cube root of x squared as x to the 2/3 power, because the index of the radical is the denominator of the exponent. So this equation could be written as x to the 2/3 equals 5. And we would solve with a reciprocal exponent, 5 to the 3/2, which is still 11.180. So we want to read radicals as fraction exponents. The index of the radical is the denominator of the exponent. On a related note with the radical business, so notice that here we have an approximate answer of 1.170. The 11.180 is also an approximation. This 125 worked out to be exact, lucky us, and then this is still an approximation. This 11.180 is still an approximation. So an added thing, for the most part right now, I care about getting you getting to the approximations. But in future, we might want to write exact answers, and exact answers are usually expressed with radicals. So this is not a separate thing as far as solving equations goes, but we just want to make a note. Not always, but exact solutions are usually expressed with radicals. Usually. We can use fraction exponents. So instead of saying but, we usually will be called upon to write a radical expression. So if we want to solve, if we're solving the cube roots of x squared is 5, we know that the answer to solve this, we say x is equal to 5 to the 3/2. And I like writing this down because this is what I'm going to ask my calculator for to get the approximation of 11.180. But we would want to write this in the exact answer. We might want to report with radicals. So with radicals, this would be the denominator is a 2, so the index is a 2. We would say this is the square root of 5 to the 3rd power. So this is an exact solution. It's the square root of 5 to the 3rd. which we might write as the square root of 125 as an exact solution. Since there are 3 5s, we might get the simplified, also want to write the simplified exact solution. So we might also want to split this up, just thinking more in terms of radicals. If we think of that, the square root of 5 cubed is a square root of 5 squared times 5. And the square root of 5 squared is just a 5 without a radical. So we might simplify this as 5 times the square root of 5. So this is the simplified exact answer. Notice that if we grab our calculator and ask for the square root of 125, so square root of 125, we get the 11.180, or if we do 5 times the square root of 5, we still get the 11.180. The 11.180 is the most important thing. So for now, your primary concern is being able to get to the approximation. And that means understanding that the inverse of an exponent is a reciprocal exponent, and that radicals are fraction exponents, where the index of the radical is the denominator of the exponent. So earlier I had said this is a variation on the do the same thing to both sides business. So it might be that we want to view things in that context. So if I have this equation x to the 2/3, so I'm going to, in this space here, I'm going to do the do things to both sides. I'm going to look at the equation x to the 2/3 is equal to 5. So when I wrote x is equal to 5 to the 3/2, I'm trying to cut out this middleman where we have to write down what we're doing to both sides. I just want to rewrite the expression in another form. In the same way that when I say 2 plus 3 is equal to 5, I can encode the same information by saying 5 minus 3 is 2, or 5 minus 2 is 3. All three of those equations contain the same information. So if x to the 2/3 is 5, then x is 5 to the 3/2. But we might come from a tradition of do the same thing to both sides. So we might want to read this as raise both sides to the 3/2 power to cancel out the 2/3 exponent. So the same thing we're going to do to both sides will look like this. I'm going to take the x to the 2/3 side, and I'm going to raise this to the 3/2 power. But if I raise the left side to the 3/2 power, then I also have to raise the right side to the 3/2 power, because we want to maintain balance by doing the same thing to both sides. The reason that we picked 3/2 is that when we raise a 2/3 exponent to a 3/2 exponent, we get an x to the first, which is what we're trying to find. So this gives us x is 5 to the 3/2, which is 11.180. Here's our approximation. And if fraction exponents are allowed, which they should be, because they are, and will be in my class, 5 to the 3/2 is our exact solution. What counts as the exact solution will depend on the person reading your work. If it happens to be me, since I'm a huge proponent of the fraction exponents, I would be like, all 5 to the 3/2 is a good exact solution. And clearly you understand what that means, because I asked for an approximation of the nearest thousandth and you got 11.180. So you know how to communicate your exact solution to your calculating machine. But from a more pedantic standpoint, it might be that the exact in fraction exponent form can also be the square root of 5 to the 3rd, which might be 5 square roots of 5. It might be that this is the preferred exact solution. This is the simplified radical form. whereas I'm fine with y'all stopping at the fraction exponent form. I like fraction exponents. Some instructors will not. Any questions? So you've heard it from me here. I'm recording this and putting this on the internet. So all you other professors that are like anti-fraction exponents, go ahead and come at me in the comments. But I am a proponent of fraction exponents. I like fraction exponents. I like fraction exponents, and I cannot lie. You other teachers prefer radical notation. That doesn't rhyme, but you know. Any questions, comments, snide remarks? I don't know if this is a thing anymore, but and I don't know if it how old or how young you have to be immune to this effect. But a lot of people my age cannot begin a sentence with "I like" without ending that with "and I cannot lie." It's just a thing. It's kind of like um, if you go to Catholic school for high school, whether you're Catholic or not, you can't watch Star Wars and see someone say "May the Force be with you" and not automatically think "and also with you." It's just can't avoid it. It just happens automatically. I don't always say it out loud, but I assure you, if you are talking to me and you say "May the Force be with you," in my mind I'm saying "and also with you." And I didn't go to Catholic church until um, we had like school-wide masses because I went to a Catholic school because they had a swim team, Catholic high school. And so my first mass was in the gym. So, and the whole school was there. And I didn't know the words. So I just kind of had to like fake it. So everybody stood up, I stood up. Everybody said something, I would try to listen carefully. But it was a bunch of teenagers, so everybody was mumbling it. So it took me a long time to figure out what the words were. Anyway, what are we talking about? Oh yes, we're talking about solving equations. We're going to read the expression, then do inverse operations in reverse order. The inverse of an exponent is a reciprocal exponent. Radicals are fraction exponent. The index of the radical is the denominator of the exponent. Any questions? Comments? Snide remarks? All right. So the other thing that we want to remember when we're doing this process, so is number 3 on our list of things, is that equations with even exponents will have 2 real solutions. Equations with even exponents will have 2 real solutions. Equations with even exponents will have two real solutions. The two solutions show up when we undo the even exponent. So for example, if x squared is equal to 9, we have two solutions, a positive 3 and a negative 3. Equations with even exponents will have two real solutions. I forgot to write down the 9 to the 1/2 power. The inverse of an exponent is a reciprocal exponent. Our calculator is not going to tell us these two solutions unless we, for some reason, set it to tell us those two solutions. If I ask the calculator what 9 to the 1/2 power is, it's just going to give me 3. So we have to know that there are two solutions when the equation has an even exponent. So for example, if we have x to the 4th is equal to 20 is fine, then the inverse of the exponent is a reciprocal exponent. So we have x is 20 to the 1/4 power. We'll grab our calculator for 20 to the 1/4 power. And we get 2.115, we'll call it, to the nearest thousandth. That's the one that our calculator will tell us. We have to know that there's another one. Because if I raise a negative to an even power, it also comes out positive. So negative 2.115. Equations with even exponents will have two real solutions. So when we say even exponents, we mean the equation where we're starting with, the equation, the exponent is an even number, 2, 4, 6, and so on. So the even exponents, that means in the equation, there's a 2, a 4, a 6, 8, or so on. If we start off with an equation and it has an even denominator, that's okay, still only one problem. It's when we do raise things to a 1 over an even power. It's when the denominator, when we're trying to solve, when the denominator is even. So the equation has an even exponent, the denominator is of the in. So if I, for example, have an equation that says x to the 1/2 power is 7. When we're solving, so this is not an even exponent. We would not count this this is not going to give us two solutions. So we're just going to solve x is 7 to the reciprocal exponent of 2, so 49. We don't get two solutions because the equation had a 1/2 power, not a 2 power. And when we're in the solution, the denominator of the exponent when we're trying to solve is not even. Any questions? All right. This does apply to equations like we did see one. I did write an x to the 2/3 is equal to 5. And so x is equal to 5 to the reciprocal 3/2. So when we go to our calculator, we should get the 5 to the 3/2. I just don't remember what it was from the previous page. And we get 11.180. We should note that the exponent here is a 2/3. which is not even. But when we look at it in radical form, if we look at this as the cube root of x squared, now the exponent is even. So that tells us we should have had two solutions in the previous problem. So even numerator in the equation, even denominator when we're solving. So we got to refine our statement a little bit. Even numerator in the equation, or an even, which leads to an even denominator when we're solving. So that's a little convoluted rule that comes from the basic idea that equations with even exponents will have two real solutions. We have to refine that a little bit to mean an even numerator in the equation. And ultimately what it comes down to is that when we're solving, we have an even denominator. So an even denominator in the solution. In the equation, the exponent is even 2. In the solution, 9 to the 1/2 power, the denominator of the exponent is even. X to the 4th is an even exponent in the equation, and it's an even denominator in the solution. X to the 1/2 is not an even numerator in the equation, and it's 2/1, so it's not an even denominator in the solution. X to the 2/3 is an even numerator in the equation, and that leads to an even denominator in the solution. And these are all numerators and denominators in the exponent. I was just trying to have to decide how many prepositional phrases it's going to be okay to line up in my clarifications. But like I said, these are all clarifications, subheadings under the big heading. Read the expression, do inverse operations in reverse order. And now we're just looking at details that go into that. One thing to note on the equations with even exponents business, if you know that there are going to be two real solutions, the two real solutions show up when the exponent with the even denominator shows up. So note, the two solutions show up when the exponent with the even denominator shows up. So whenever you apply the even denominator exponents, that's when the two solutions show up. Let's look at a couple of examples. Let's suppose that I have x to the 4th minus 5 is equal to 20. Let's do our normal plan. We read the expression, then do inverse operations in reverse order. Let's also, if we were just encountering this for the first time, we would notice that there's an even exponent in the numerator of this equation. So we know we're going to have two real solutions. So we have to keep in mind that the two solutions show up when the even denominator exponent does in our solution process. So we read the expression, and to turn an x into a 20, first we raise to the 4th power, and second we subtract 5. So our solution plan to turn a 20 back into an x, first we're going to undo the subtracting 5 by adding 5. And second, we're going to undo the 4th power with a 1/4 power. Oops, spelled 4 wrong. There we go. So here in the second step, this is when the two solutions will show up. When we do this 1/4 power.
So we grab our calculator, and the first thing we have is 20 plus 5 is 25. And then the next step is 25 to the 1/4 power. We're doing the even denominator exponents, so 25 to the 1/4 power is 2.236, and this is where the two solutions show up. So there's a 2.236 and a negative 2.236. Since this was the last step, we're done. And we have these two solutions that happen to be opposites. So x equals, our approximations are 2.236 and negative 2.236. The last thing we did was the 1/4 power, the even denominator exponents. So that's all we had to do. We just write down our two solutions, one positive, one negative. Let's compare and contrast a variation on this equation where I use the same two operations, but I change the order with some parentheses. Now we're going to be reading a different equation. To turn x into a 20 in this equation, first we subtract 5 and then we raise to the 4th power. So to undo this this set of operations, we'll start with 20, and first we'll do the 1/4 power. This is when the two solutions will show up. And to both of those solutions, we're going to have to invert the minus 5 with a plus 5. So now the two solutions are going to show up in the first step, and we have to add 5 to both of them. So we'll start off with 20, and we'll raise 20 to the 1/4 power. We did that previously. It's 2.115 and negative 2.115. I'm going to load it on the calculator. So 20 to the 1/4 power is a 2.115. Then to both of these numbers, we have to do the second step. So I have to do 2.115 plus the 5 to get 7.115. And I also have to do negative 2.115 plus the 5 to get a 2.885. So once we undo the even exponent, once we're solving and the even denominator exponent shows up, that's when we have to split the problem into two solutions. One for the positive and one for the negative. So now our solutions are 7.115 and 2.885. A lot of times we'll mark this with a plus or minus, but that doesn't mean that one's always going to be positive and one's always going to be negative. Here we ended up with two solutions, but both the solutions were positive because the first thing that happens is that we subtract 5. If we check both of these answers, we take 7.115. If we take 7.115 and then subtract 5 and then raise to the 4th power, we get 20. And then 2.885 if we subtract 5 and then raise that to the 4th power, we get the 20. So notice that when we're checking our answers, when we get to raising to the 4th power step, we're either taking 2.115 to the 4th power to get 20, or negative 2.115 to the 4th power to get 20. So when we're checking, there's a positive and negative, and the positive and negative end up at the same place. So those are the things that we want to remember at this stage in our solving equations career. We'll want to read the expression, and we want to do inverse operations in reverse order to solve. We want to remember that the inverse of an exponent is a reciprocal exponent. We want to remember that radicals are fraction exponents, where the index of the radical is the denominator of the fraction exponent. We also want to remember that equations with even exponents will have two real solutions. And by even exponents, that means an even numerator in the equation, so that when we're solving, we'll get an exponent with an even denominator. And in addition to that, we have to remember that the two solutions show up when the even denominator exponent shows up. This only seems like it's a lot to remember because it's a lot to remember, and you have to remember all of it all the time in perfect detail. So it just takes practice. All right, that's going to do it for today. So we'll see you all tomorrow. Everybody have a good day, and thanks for playing.